Yifan Hu, Contextual Bilevel Reinforcement Learning for Incentive Alignment.
Thank you for the introduction, and thank you so much for inviting me to come to this nice workshop. Listen to many of the amazing talks, and some of them are actually closely related to what we plan to do. So today, what I'm going to share with you is actually two works. So on contextual bilevel reinforcement learning. So let me start with what do I mean by bilevel reinforcement learning. Okay, so this is the outline of the talk. I will start from the modeling, and then I'll talk about algorithm design from optimization perspective, and then how it involves into the reinforcement learning setting, and it give you a summary. So in the beginning, I think many of the times in optimization and in game theory, we talk about stochastic bilevel optimization, and you can simply think about it as a Stackelberg game, meaning that there's a leader and there's a follower. And the leader makes some decision X, the follower observes the leader's decision, the follower is going to make a best response Y star for given X. In this type of regime, leader and follower might have its own objectives, right? So their utility may be different to each other, okay? And this order actually makes a big difference because if you have this type of order, of course, it will be difficult to find a Nash equilibrium. And this type of problem has many interesting applications, static ones, coming from hyperparameter tuning. Let's say how you tune a hyperparameter when you train a neural network. Let's say neural architecture search means that the leader wants to find a neural network structure that is good. And then given the structure, the follower is going to train the neural network, find the best parameters. Similar things also happens in Stackelberg genome game. And this is actually a very versatile framework and has been studied in many, many fields in different names. What we're realizing is that this type of framework doesn't capture two very important scenarios. The first scenario is this, what I call it optimization with side information. So what do I mean by side information? Imagine you are facing some systems that are given to you, given by the leader, okay? And when you make your best response may not always be static. Your best response could depend on what are the current realization of the global randomness. And let me give you some examples. Say, for instance, the leader is the designer of your city, the road map in your city. And given this road map, you can choose how you go from home to work, right? But the route that you're going to choose probably also depends on the weather situation of that day, right? So that's what I mean by the randomness here. Similar things could also happen a lot of times in operations research, in machine learning. So basically, this randomness could affect how the follower make their best response. So the best response may not only depend on the leader's decision, but depends on this realized randomness. Okay? It has many interesting applications, a lot of times coming from robust optimization and learning, and also this so-called integrated estimation and integrated learning and optimization, because many of the problems are like, you need to learn some parameters or learn some models and then plug it in to do your decision making. So all this type of problems can be formulated this way.
For the third motivation, the downstream decision-making task is
The downstream decision-making task is usually the follower, and then the leader is usually about estimation, yes. I'm going to show you some more examples. The second case is because the classical problem only have one follower, right? A simple generalization would be, very intuitive generalization would be if you have multiple followers, what is going to happen? And imagine, say, you are YouTube, you make recommendation systems to all of your users. And of course, your users have different preferences, and whenever you change your recommendation systems, the response of the users is going to differ from each other. Of course, you cannot do personalization for all of the users, but at least you can do some kind of clustering. And in this type of regime, the classical optimization or bilevel optimization doesn't capture this. And in machine learning, this is quite relevant to this so-called meta-learning or multitask learning, that each of the tasks is different, but they share some similarities. Each of them may not have sufficient data to train a big model, so you try to aggregate the information, and then train an aggregated model on the leader's perspective, and train each tasks that are not too far away from the aggregated model. Okay, to capture these two scenarios, actually we propose something called stochastic bilevel optimization, but in a contextual way, and the context is really the I use this. The context is really this psi here. And in the past, your follower's best response does not depend on any randomness. It's just a best response to the leader's decision. Now it depends on this context. And if you're familiar, minimizing conditional expectation is actually called contextual stochastic optimization. It's quite relevant because we have this type of contextual problem in the lower level. And then today we're going to focus on when the lower level is strongly convex for the contextual bilevel problem. Okay, so meaning that this G function is going to be strongly convex in Y. This, of course, if it is not strongly convex, the optimal solution may not be unique, and then you have a lot of issues. So you need to redo the modeling. So just for the sake of convenience, we just focus on the strongly convex case today. Okay. And now let's think about it. This is bilevel optimization or contextual bilevel optimization. It's still in a static case, right? So what happens when you have a dynamic scenarios? And today, what I'm going to focus on Markov decision processes, finite state, finite actions, and then transition kernel reward. Everything's so kind of obvious to you guys after so many talks. And we are trying to maximize some reward given all these MDP environments. So a lot of times when we talk about reinforcement learning, people were thinking about how I train. Let's suppose the environment is given to me, and how I train an agent that finds the optimal policy, right? But in many of the situations, the environment is not coming for free. Let's say you have some applications coming from autonomous driving. How would you define your reward function, right? So a lot of times, actually a lot of practical scenarios, people really need to think about how I specifically design an environment of the MDP, and then given this environment, how am I going to train the agent so that it behaves in a way that we want them to behave. So that's the idea of proposing this bilevel reinforcement learning. It has many different names. In the beginning, one of the earlier work called it model design for MDP. And there's a lot of work on inverse RL that tries to learn a reward function from observational trajectories. And there are also many works about imitation learning, meaning that you don't know what is your objective, but you have some experts demonstration and you want to mimic it. All of them kind of somehow can be formulated as this type of bilevel reinforcement learning problem, as I will show later. But today we're going to focus on the case when we are the environment designer. And particularly we are considering parameterization regime, meaning that we are trying to design some environment that are parameterized by a parameter x. In addition, this x can parameterize your reward, can also parameterize your transition kernel. In addition, we also have this context here. This context, as demonstrated earlier, it can be some side information, right? Because when you solve a reinforcement learning, there might be some side information that influences the environments. There could also be multiple followers. So when you formulate these bilevel reinforcement learning problems, the designer is going to design the environments, and then it's taking the optimal policy of the agent that learns the environments into its consideration in its objective. And then the follower is going to just, given this environment, try to solve entropy regularized MDP problems. Please.
Just think about this for a moment. This makes you think about contract theory, where there is sort of.
I'm going to show you it's relevant. It's relevant. Yes. Yes. So in this work, I'm just making it simple. Simple in the sense that because this is a bilevel optimization problem, it really matters which. If you don't add entropy regularization here, you might have multiple optimal policies. And at multiple optimal policies, you need to decide which optimal policy you are going to use for the leader's objective, and then that would introduce another layer of optimization problems. So adding this entropy makes things much simpler, and then in the paper we have shown that adding this entropy, you are not too far away deviating from the without entropy. So
you benefit from this or better optimization than convex?
you don't have convexity still. Even by adding this entropy regularization, you get uniqueness, but you still don't have convexity. So that's why I'm saying non-convex here, because the lower level is still going to be non-convex. And that's another layer of challenges because now you need to solve a non-convex optimization problems to global optimality. Okay.
But, I mean, I assume you get uniqueness because you basically are removing corners.
Yes, because of the entropy reorganization.
Yes.
Yeah. Okay, and the interpretation, right? Single agent, because C basically reduces to a degenerator, degenerates random variables, and then you get a single agent. It's just to design MDP environment for one agent. When you have multiple agents, each may have its own reward that you cannot see, but you can actually incentivize them by a central reward that you create. And then the contextual RL is that C encodes the global uncertainty. Right? So many applications of this bilevel reinforcement learning. First one is going to be reinforcement learning with human feedback. I'm going to show you the formulation later. It's actually used in alignment step of large language model training. And as just mentioned, it's relevant to contract design. It's relevant to reward shaping in like principal agent problems, particularly in the dynamic sense. And it's also relevant to mechanism design problems. Okay? So I'm going to show you some more detailed formulation. And I think Michael, or I don't know how to pronounce his name correctly, he already mentioned this reinforcement learning with human feedback, right? So basically, it says that if you have a language model, you already train a base model, but it doesn't give answers as human preferred. And how would you tune it? When you tune it, the basic thing to do is that you ask one question to this base model, let it generate two answers. Once you have these two answers, you send these two answers to human labeler to say, which one do you prefer? And human labeler will tell you, I prefer the YW means the means the winning one, and the YL means the losing one. And then send this preference data. You're going to use this preference data in the classical training. You are going to use this preference data to learn a reward model, and this is relevant to choice modeling. That's the so-called this Bradley-Terry choice model. It can be reformulated basically as a softmax type of form. And then once you get the reward model, you're going to fine-tune your base policy by maximizing your reward model under the regularization that your new model should not be too far away from the original one, so that you keep so-called language grammar and everything. Okay. And how is it relevant to bilevel reinforcement learning? In particular, if you get two feedback, let's denote it as trajectory tau 0 and trajectory tau 1. And let's say human labeler always say, I prefer tau 0 than tau 1. And then you can formulate this reinforcement learning with human feedback as a bilevel problem. And the upper level is trying to maximize the log probability that tau 0 is preferred than tau 1. And then the lower level is going to say, my pi is going to be the policy that generates these two responses, such that it will maximize a reinforcement learning problems. Okay? And in particular, this Bradley-Terry model will become, on the reinforcement learning setting, will become a softmax over the discounted reward of this reinforcement learning. Okay? So this is a paper in 2017, I believe, 5,000 or 6,000 citations. And then moving away from machine learning is also quite relevant to econ type of topics like principal agent problems. Let's say you have a principal that wants to incentivize your agents to with certain state actions, right? And then in this type of scenarios, probably your principal could design a reward for everybody. But of course, this CASI here, let's say you have multiple agents and this CASI is just discrete, meaning that each agent could have his own intrinsic rewards, meaning that this is the reward he would receive for himself. And then you want to incentivize them, right? So you have this reward here, and this reward is designed by the leader. And this can be formulated as principal agent problems. It's also quite relevant to, as I said, contract design, tax design, mechanism design type of problems. Okay? Please.
So here you're assuming that the agent maximizes the combined reward of its own and the principal?
No, so this is the reward. For example, if I do something, I get a reward. This is some reward I know for myself. Nobody else knows about it. this is a reward that the principal is going to release to the agent, saying that if you visit this state action pair, I'm going to give you this additional reward. And total together becomes the reward for this agent.
So it's like a dynamic contract. Okay.
Yeah, it's like a dynamic case. And then this R bar here means that, because the leader needs to give some reward to the agent, this R bar could be something, like the minus of this incentivized reward given. Okay. And then it can also be utilized to do robustness. And in particular, can be utilized as an adversarial environment generator. So because when we train reinforcement learning, a lot of times we only have, good performing data. Let's say in autonomous driving, you just see experts demonstrating how to drive the car smoothly without not many crashing. In this type of scenario, when you want to test your policy, you really want to have a simulator so that it tests things in a robust way, in an adversarial way. And then if you formulate the leader's objective to be like choosing the adversarial transition kernels, parameterized by your design parameter X, and then choose this objective to be negative of the cumulative reward of these RL problems, then your overall objective is to do a min-max problem. And this min-max problem is basically trying to find the parameter of the worst case transition kernel for your MDP. Okay, I hope that I have well convinced you that this is some problem of interesting. And let's move on to the algorithm design part. And I will start from optimization because this will make things easier. In the optimization, of course, we want to utilize some kind of gradient-based methods. And then the first thing we need to do, or we need to understand, is how do we get a gradient? And if you write it down in hypergradient form, let's say because the lower level is unique, it's strongly convex so that the global optimal solution is unique. And then you'll be able to know that this optimal solution Y star is going to be unique. And then you can use implicit function theorem to write down everything about this gradient of Y star with respect to X. The gradient of the optimal response with respect to the leader's decision. And it's complicated. You don't need to read, but this is a Jacobian. This is a Hessian inverse of the lower level problem. So once you have this type of form, another thing you need to do is try to estimate it, right? And then there are two challenges here. The first challenge is that you need to estimate a Hessian inverse. Complicated. The second challenge is that for each given leader's decision X and the random realization C, you need to find an approximate good best response. And for the Hessian inverse part, I'm going to skip it. Basically, what you do is that you can, you can first normalize your Hessian inverse. You can first normalize, and once you normalize a matrix to be positive definite, and then smaller than identity matrix, you can write it down as a Newman series. And then you truncate at a certain level. Together with important sampling, you will be able to build an estimator that is good enough. So this is the form. You just write it out. And then you truncate at a certain truncation level. And then you replace this matrices expectation of A with IID samples. The good thing about this is that the bias of this estimator usually decreases quite fast, exponentially fast in terms of the truncation level. So together with important sampling on this part, you will be able to get a good estimator. The second challenge is much more interesting, and because if you see from the modeling perspective, from the bilevel problem to the contextual bilevel problem, all I add is that I say the lower level problem has to be, the optimal response has to depend on a random conceit, right? And this seems to be quite small change. What makes things difficult? What makes things difficult is like this. Imagine if you don't have this context here, and then the best response is going to only to depend on the leader's decision. Under some kind of regularity assumption, you can think about, the follower of the best response of the follower, given a leader's decision, could have some kind of stability. Meaning that if the leader does not change its decision too much, the optimal response will not change too much as well. And that means if I have a good estimator of the best response at the current iterate, for the next iterate, I don't need to retrain from scratch. Because I can leverage the estimator for Y star xt to help me build an estimator for Y star xt plus 1. Things are difficult here if you have this context. Why? Because once you have this context here, this context will be realized as a random variable at each iteration. And then even if xt and xt plus 1 are close to each other, this randomness will destroy this type of stability so that you need to retrain from scratch. So that's why we are thinking, okay, naively, let's just run some gradient methods on the lower level long enough so that it will give us approximately good optimal response. And that's why we'll adopt this epoch SGD. It's very simple. You run SGD in epochs. In the first epoch, you run 2-step. Second epoch, 4-step. Kth epoch, 2 to the power of k steps. We are using it mainly for the purpose of analysis. If you use just naive SGD, it still works. Okay. And once we get this, we have everything. We build a hash inverse estimator. We plug in this good approximation of the best response to inside. And this estimator has a nice property that the bias is small. It's nearly unbiased if your truncation level and the number of epochs is going to be logarithmic in terms of your 1/, accuracy. Okay. The challenge is really that even if this number of epochs is logarithmic, because in each epoch you run exponential number of steps, so eventually you still run polynomial number of steps to get a good approximation of the best response. And to avoid this, because this is the additional complexity that comes into the picture because of this context. Okay? So to avoid this issue, we actually leverage some techniques that actually Jose created in 2015 together with Peter. So one thing you could do is that you can leverage this so-called randomly truncated multi-level Monte Carlo estimator. The idea is like this. This is the estimator you want to build. You just write it as a telescoping sum. Nothing too difficult. You multiply pk, you divide pk. Nothing too difficult. And then you say you let pk sum up to 1 and be non-negative. This forms a probability distribution. And then you can utilize this highlighted estimator as a good estimator for the original base estimator you built, right? And this is called the multi-level Monte Carlo estimator. And what I'm doing here, I do a truncation, so it's not exactly what, because Jose proposed this unbiased one. I'm using a biased one here. And then the good thing is that now you have additional control because you can design this probability distribution. Usually you use some kind of truncated geometry distribution so that with very large probability you generate a small k. And now when you build this highlighted estimator here, 1k is small, it's quite cheap to build it. And with very low probability you generate large k to correct the bias. So the expected number of iterations you need to run originally is 2 to the power of k. Now in expectation is linear in capital K. So then you get a great reduction from polynomial to logarithmic. Okay? And then you might question me because I'm dividing this huge pk, this pk here, and this pk can be quite small if k is large. So that's why for this type of methods to work, you really need to ensure there's a variance reduction effect or control variant effect such that yk plus 1 and yk are close enough so that they can cancel out the negative effect of dividing this small pk here. So that's why we require this, this estimator to be Lipschitz continuous. But nevertheless, if you have this type of results, then you can show if the lower level problem is strongly convex. If you use these double loop methods, the complexity bound is worse comparing to non-contextual setting. But if you utilize this multi-level Monte Carlo type of gradient estimator, you can get a complexity that is logarithmic worse than the non-contextual setting. Okay? It's just logarithmic. And in terms of sample complexity, if you ignore this logarithmic term, it's optimal. Okay. Given this on optimization, we also did some experiments on meta-learning. The message is basically that you want to solve the lower level problem to better accuracy, and then you get better test losses on the leader's objective. But increasing k will have increasing k you need to run many lower level iterations, so it's going to be costly. And then we show that when k is large, you can get a very significant acceleration utilizing this multi-level Monte Carlo estimator. Okay, now, since I have explained how do we do bi-level optimization, I think things are could be similar for bi-level reinforcement learning, right? If you treat reinforcement learning as an optimization problem, as a policy optimization problem. But things are not exactly the same, it turns out. It turns out that there are many constraints. So I'm listing a few here. So first of all, let's say in the incentive, if you give incentives to followers visiting certain state actions, the leader will not know the followers' intrinsic reward. It means that the leader may design the environment, but it does not know the full picture of this MDP environment because each follower could have its own intrinsic rewards. The second thing is that in the optimization, we know how we solve the low-level problem. We're using SGD to solve it. But in practice, for reinforcement learning, if you have some agents, you will never know what type of algorithm it uses to solve the MDP problems. You just see what are type of trajectories it generates under its own policy. The third thing is that the follower itself may not know its own optimal policy, especially in econ type of problems, right? The follower just know, okay, I'm rational people, what I do is actually maximizing my reward, but I actually don't know what is my optimal policy. So the question that I think is relevant is, what if the leader can only learn how to make better design of the MDP environment, but you only using the trajectories generated by the followers. Okay, so this is very different from optimization, because optimization, you are like the god that you can control everything. Okay, but still, trying to fulfill all those requirements, you need still a gradient estimator that you can just estimate using, under all these type of data limitation constraints. And very interesting, as I showed you before, right? So the difficult here when you compute the hypergradient is really that you need to take gradient of the best response with respect to a design. And in a bilevel optimization, this is relevant to negative Jacobian multiplied by hashing inverse. It turns out that in bilevel reinforcement learning, taking the gradient of this optimal response does not need any second order information. And this is quite different from bilevel optimization. The reason we realize is that once you add this entropy regularization, you can show the optimal policy is actually proportional to exponential of your optimal Q functions. And the optimal Q function is going to, and that means that the lower level problem, you can throw it away. You can just plug it in this. Of course, we need the normalization terms inside the objective, so everything becomes a compositional optimization problem instead of a bilevel problem, okay? And utilizing this observation, we were able to derive the hypergradient form. You don't need to read it, it's very complicated. But basically, there's a way that you can derive it, and that there's a way that you can use trajectories to estimate it. Now, the second challenge is really that previously we say in optimization, we want the lower level problem to be strongly convex. If it is strongly convex, you know that the stochastic gradient methods will converge globally quite fast. But now, even with entropic regularization, you know that the reinforcement learning problem, if you formulate it as a policy optimization, is going to be non-convex. Of course, this is finite state, finite action, value-based methods will still work because it will have contraction properties. So what we are demonstrating here is that actually a lot of the infinite horizon discounted MDP or linear quadratic regulator type of control problems, they are not that bad. They're not that bad in the sense that they either admit this so-called hidden convexity. Hidden convexity basically means there's a transformation to make it into a convex problem. They could also admit some kind of benign non-convex landscape, and this table basically summarizes that. In different regime, finite state, finite action, continuous state, continuous action, infinite horizon or finite horizon MDPs, this type of benign non-convex landscape has been established. So you can actually leverage this benign landscape to show that even if you try to solve the non-convex problem using policy gradient type of methods, you will still be able to find global optimal solution quite efficiently. In particular, this is our results, and this result actually covers, we show that in this result, we propose some framework that actually covers linear quadratic control. So basically, you can directly use our framework to show that. And it's slightly more general than what people do directly using the special structure of linear quadratic control. Okay, given this, we can safely assume that we assume access to an oracle of a data optimal policy, and this oracle will generate trajectories for us to use. Okay? And now I'm going to discuss a little bit further because in the hypergradient form, that you will still realize that the leader needs to define its objective function, and the leader needs to take gradient with respect to pi star. And that part, you will still need some information about this optimal policy. But if your leader or your designer's objective is very special, it's related to the MDP that the follower is playing. And specifically what I'm saying here is, let's say, the leader knows the reward and the transition, and then it tries to maximize this type of rewards, and this type of rewards comes a lot from this principal agent problems because you are incentivizing them. And this basically means that the leader also faces MDP, but this MDP, you know the reward, you know the transition, but the trajectory is generated by someone else. The trajectory is generated by the follower. And this type of regime, then you can show that the hypergradient does not involve this pi star, and then you can now fully use the trajectories to estimate the hypergradient and try to run your algorithm. And eventually, so far everything here is agnostic. Agnostic means that we are only assume access to oracle that generates trajectories. We don't need to know how the agent learns the optimal policy. Either methods you can use, value iteration, policy gradients, all kinds of methods you can use. But now, if you can control it, can we further accelerate it, right? If we, as the leader and follower, they're collaborating with each other, can we accelerate this type of training procedures? And of course, we still want to utilize this multi-level Monte Carlo type of estimators to help us. And here we face a lot of challenges. As I described in optimization, right, for this type of estimator to work, you really need a control variant effect. That this neighborhood difference needs to be small enough so that you can hedge against the negative effect by dividing the small pk. So yk plus 1 and yk needs to be close. Okay? But in reinforcement learning settings, you will be able to see that when we estimate these hypergradients, we are using trajectories generated by near optimal policies, right? And then if you generate two trajectories, let's say we use two trajectories generated by pi hat k and pi hat k plus 1. Obviously, even if they are close to each other, the randomness in generating these trajectories will be different. And as a result, the control variant effect will be losing here. So you cannot directly utilize this type of multi-level Monte Carlo gradient estimators to help you achieve acceleration, even if the leader and follower are in collaboration. So in the paper, we are using mini batchings and all kinds of other techniques to ensure that we can achieve the acceleration. Okay? So to summarize, I think I've introduced to you this contextual bilevel optimization framework. This is a paper published 23 in Europe. So how do you do hypergradient estimation? How do you do acceleration? How do you ensure that this can be applied to all kinds of different application scenarios? And then, very naively, we thought bilevel reinforcement learning would be something similar, but it turns out that they are so different because of data limitations, because of all kinds of the environments you need to think about. And to take away messages, right? So bilevel reinforcement learning, you don't need second-order information. You can learn, you can adjust the model design without knowing how the lower-level problem is solved, and then you can accelerate. This is a paper published in 2024 on NeurIPS. And then some future directions. Okay, so the first thing is that if you can think about what we are doing here now for the bilevel reinforcement learning, even if we have multiple agents, these agents are actually not playing together, not playing with each other. They are playing only through the leader, right? Because when the leader changes the design, the follower is going to behave differently. But they are not interacting, so how would one incorporate interactions between lower level agents? The second thing is that from the econ theory, a lot of times in mechanism design, you have all kinds of this incentive compatibility or this individual rationality type of constraints. And of course, what we are doing here for bilevel reinforcement learning, so far we didn't incorporate anything like this. And let's say one scenario is that because in this hypergradient form, we still need to take this gradient here. And that means the follower, if it's a general objective, if it is not some MDP type of, if it's a general objective, then the follower could actually try to mislead the leader by reporting not his own, but not reporting truthfully, right? I can report a policy that I'm not really using to generate my trajectories. So how you hedge against this type of issue? Of course, you need to incorporate some kind of incentive compatibility constraints into the bilevel reinforcement learning problems. And then, of course, how do we further do robust and safe reinforcement learning and reinforcement learning with human feedback? Just a quick advertisement, because my colleague and I are hiring a postdoc, so if you know any good candidates, feel free to let them contact me, and there's a Google form on my homepage that you can submit your CV. And these are the collaborators. Vincent is from ETH, and he's doing an intern at Google DeepMind at the moment. Bana and Andres are also from ETH. Andres is my postdoc advisor. Georgia is now an assistant professor at the University of Zurich, and I moved from ETH and EPFL to Rutgers University. Thank you so much.
Any questions? It appears that there are many questions involving robustness to the
Yes.
Gradient, robustness to the response of the followers.
Yes.
For the first one, for example, is the algorithm robust to the sample data that you obtain?
So far, in optimization, you mean?
Right, yes.
So far, it's not. So far, it's not, because we didn't incorporate any kind of robust formulation inside it at the moment. I would say these two bilevel forms are more for modeling certain type of robust problems. But always think twice before you use it, because this is a very much more general framework and much more general modeling. You might lose some structures if you use it in type of robust problems. But it will basically provide a kind of a baseline that you can always run this type of methods for your robust problems and see how it performs. Yeah. Please.
Suppose there is some kind of way you can do a controlled variant on the trajectories you generate from the policy.
Yes.
Does that lead to a reduction? Because now you can...
That will also lead to reduction. So far, we are not making this assumption. We are using some other techniques, basically mini batch, trying to utilize them.
That degrades your complexity.
You need some additional tricks in terms of how you sample trajectories. So because eventually everything is measured by how, it's not just about how many trajectories you generate, it's also about how many steps you generate. So there are some tricks there. So you can also call it measurement in a sense.
Thanks.
So for the RL reduction, this really relied on how you having the entropy to have the strong convexity and the explicit form of pi star, right? Because that essentially, so it's this sort of, it's this beauty of entropy that you get explicitly the pi star, right?
Yes, that defines unique optimal policy.
Yeah, but one which is accessible explicitly, right? You know that pi star is proportional to the Q function.
Yes.
It's not that.
Yes.
So have you considered any other penalties there that, I don't know, pi divergence?
We didn't. I believe that you can use other penalties as long as it ensures uniqueness. It should work. Of course, you need to still ensure that even after you adding this penalty, you need to ensure the non-convex landscape is still there. Okay, so.
Yes, but if you don't have this, but then you would have the Hessian or whatever appearing in there. You have to use the business function here, right? So.
Yeah, that's possible. That's possible. If you use a different regularization, it's possible that you still need to treat it as a bilevel problem, and you cannot use the composition form, and then the second order information might get into the picture. Yes. So far, this one does not. I think that's very special because of this entropy regularization. I believe there's one paper considering didn't adding any regularization, and then so it means that you don't have this term here. And then the optimal policy, you could have multiple optimal policy. They were discussing kind of pessimistic selection and optimistic selection of the optimal policy into the objective. Yeah.
Any final questions? Let us thank Yifan one more time.